I will discuss the problem which probably everybody in the room knows. It's more or less with us since the discovery of superconductivity in 1911. That's why kind of I more or less counted years. What do we know at year 114? And how actually we can answer the question properly. First, well, okay, what is the big question we're trying to resolve on a big scale without kind of any further details? Well, currently we have the following situation. So most material science code, I'm not saying just all of them, but the majority, they're just doing TC using the following setup. You assume some electron-phonon coupling, and then you introduce more or less, and I'll explain, sometimes even calculating, but I'll explain, okay, what's the problem. You just produce something which is repulsive pseudopotential, which is reducing the amount of electron-phonon coupling for superconductivity, and you get TC out of this scheme. Okay, so if I ask a question if electron-phonon coupling is very weak, say smaller than the current more or less known value of mu star, roughly 0.1, there is no TC. And then you say, okay, well, there is also another community which is constantly looking for alternative mechanism. Alternative means there is no electron-phonon coupling, and you still have TC. And this is becoming a little bit incompatible, more or less, for the current situation, that without electron-phonon coupling, this part says there is no TC. At this point, I'm not saying how high or how low, but still kind of it's a little bit a contradiction that looking for alternative mechanisms cannot easily project on what is done in material science code. So for this, you say, okay, well, maybe we need some better machinery to understand how actually mu star is calculated. Can it actually change sign in some cases? Because for alternative mechanism, it has to change sign. So whatever comes from Coulomb interactions ultimately has to give you, because we don't have any other. So more or less in any mechanism, we count only Coulomb interactions and electron-phonon coupling. We don't kind of consider anything else. Everything else is emerging from those. So somehow kind of this part has to penetrate into the first part. Yeah. So just while that's on a big scale, we have to understand how mu star happens to be and how to compute it. Of course, well, you start somewhere, which is relatively kind of simple model. I will discuss homogeneous electron gas, where we can finish the job and tell you what mu star is and what kind of misconceptions were happening historically. Well, okay, that's more or less what I am going to discuss, because so far, even for the homogeneous electron gas, my claim is it was never even computed with control method. So. Yeah, S-wave. Yeah, S-wave. Yeah, so first, let me kind of mention known collaborators on the project, because there are some unknowns, which I still didn't get the names. So those are Tao Wang, Shanshan Kai, Kun Chen, Andy Millis, and Boris Svistinov. And it's a very long effort for many years, because we started from knowing nothing, then knowing better, then having better understanding, still not being able to finish the job. Now I think we have the understanding, the protocol, and we can finish the job. So what's the history? So why I'm even talking about this now? Okay, since 1911, for a while, okay, there was a phenomenon, but not clear understanding what and why. Well, but after the discovery of superfluidity in helium-4, clever people start realizing that maybe there is something like two-fluid model. London equations showed up. So people were kind of implying that something behaves just like in helium-4 as a charged condensate. And they just were using phenomenological equations kind of to explain some properties of superconductors. But the answer was, sorry, electrons cannot pair. You have Coulomb repulsion. And this was a puzzle for more than 40 years. Well, then came small piece of understanding that, well, if electrons can actually exchange phonons, this results in an attractive interaction close to the Fermi surface. And what theorists typically do, they just throw away the biggest problem, so which is the Coulomb repulsion. It was bothering everyone for 40 years, but let's stop bothering. And so that's the BCS. Say, okay, well, let's electron-phonon coupling gives you attraction. Let's forget about Coulomb repulsion in the first place, and you produce an answer. And then undeniably, the theory, especially if it's expressed in terms of TC itself, and you scale everything with TC, there is undeniable proof it's a correct calculation. Well, at this point, some people immediately started wondering, okay, well, yes, you have electron-phonon coupling, which is attractive, but we still have Coulomb repulsion. Where did it go? And very quickly, within, I know, a couple of years, Bogolyubov, Cherkov, and Tolmachov, they introduced the theory, more or less explained as follows. They say, okay, yeah, maybe you have some Coulomb repulsion at very high energy scale. For example, screen Coulomb interaction. This is Thomas Fermi screening momentum. Well, and then if I consider a Cooper ladder with repulsive interactions, I discover that at lower energies, capital omega, this renormalized interaction actually scales down and maybe even suppressed by a large log, because between Fermi energy and Debye frequency, we have a large energy scale. And you see more or less, not much depends on this parameter, so it's roughly divided by log. And the log is maybe several hundred. This explains, if I just simply plug in this construction times the Fermi energy density of states, don't think much, this is just 1/2. Universal number, not even RS dependent. You substitute 1/2 into this formula, you get 0.15. Start using it for all materials without thinking, and if you slightly miss something, you are allowed to tune this number between 0.1 and 0.2. More or less in the majority of situations, that's roughly the range. Looks like everything is working. And then there was, of course, Macmillan's formula, which was saying, okay, yeah, looks like this type of phenomenological treatment is working and explaining huge number of superconductors. Looks like, yes, Coulomb interactions, according to this scheme, can be reduced to mu star. Everybody was happy for a while. Well, this is now known as probably Anderson-Morel pseudopotential, but all they did is introducing a notation. So the job was done by Bogolyubov, Shirkov, and Tolmachov. Well, but then, well, this is 1978. Then it was repeated by Rachel and Sham, same Sham as Consham, several years ago. We did the same type of calculations extensively in many different situations, and we fully confirmed that what Takada, Rachel, and Sham found is correct. They say, okay, all this reasoning is total nonsense. None of this is true, because the moment you go from radical mistreatment of Coulomb interactions as completely screened at all frequencies, and you actually do a better job, you do a dynamic RPA. You say, okay, screening is a dynamic process, let's do dynamic RPA. They actually found that mu star, if you compute it honestly, as everybody was thinking according to the scheme, you should do it, you get mu star less than 0 for RS bigger than 2, which is almost all materials. So which means they undeniably proved that the entire reasoning here is wrong. Looks like Coulomb interactions are not even the enemy, it's the pairing glue. And that brings us to the problem. Okay, yeah, but the entire evidence for a huge number of experimental materials says mu star is repulsive. The reasoning why it's repulsive, it's not this one. That's totally wrong. According to better calculations, it has to be negative. And everybody knows that if you start using negative, your TC will be, I know, too high, by a factor of 5 or by 2 orders of magnitude. So which means we do have a problem because we have no control whatsoever at this point what the actual value of mu star is and why it comes to be this way. So we have to answer the question, and you ask, okay, what's the resolution of the contradiction? And the answer is very simple. This is just one of the mistakes. And there are several more mistakes which you do on the way, one after another, one after another. Roughly all mistakes are by a factor of 2. At the end, most of them just cancel out to nothing. And that's kind of more or less the conclusion, which I will come to the end, but the story is more important kind of than the final result. So yes, the contradiction is resolved now because you can compute mu star honestly and properly, and I'll describe the protocol. And turns out that yes, it's 0.15. So, but not by this reasoning. Okay, so what else we have to consider apart from talking about interaction glue? Well, the first thing, which is typically completely omitted in most kind of calculations right away, because if you use mu star, it looks like you only modify the coupling constant, but you don't change the properties of the Green's function. You say, wait a second, if I have an interacting Coulomb system, especially if it's strongly correlated, how can we ignore that interactions in the Fermi liquid, they renormalize the Green's function? So it's no longer kind of simple pole. It has self-energy, which is also frequency dependent. And we know that, well, at the end, say occupation numbers for electrons, they don't have a unity jump at the Fermi surface. It's reduced to Z. Z is less than 1. It's only for quasi-particles you have universal jump 1. But for real particles, it's Z. It immediately tells you that, okay, well, the Green's function has regular part, which is completely smooth across the Fermi surface. And then you have a singular part, which produces the jump. And this singular part is Z divided by some renormalized spectrum. So in the BCS theory, if you start kind of writing it down, you see that, well, that's the crucial object which gives you instability. The product of two Green's functions which you sum through momentum and frequency. Well, the regular part in this sum gives you a constant, but what drives the BCS transition is the log. But the coefficient in log, just, well, see, that's the regular singular part which gives you the log. This singular part will come with z factor squared and renormalized density of states. So if I use bare density of states, it's renormalized by the effective mass divided by bare mass. So this factor is in front of the log. So everybody understands that, okay, well, TC will be exponentially sensitive to everything in front. And if you are missing here a factor of 2, you're completely off in your theory. BCS theory with mu star, Migdal-Ashberg theory with mu star, is totally ignoring this coming from Coulomb interactions, because it's not even part of the theory. So you start wondering, question number 1, what is z squared, what is m star divided by m? How much are we missing if we actually start doing the job? I will say right away that all my answers will be for homogeneous electron gas. That's more or less, I know, the foundation of density functional theory. You start with energy as a function of density, and then you just try to move forward. So our calculations can be finished for Gellium. We didn't do anything yet for more sophisticated cases, but I will explain the protocol, which potentially, if implemented in other cases, will give you the mu star. Okay, so this is all for homogeneous electron gas. The results will be for homogeneous electron gas. So that's what was done by the first time by the variational diagrammatic Monte Carlo methods, which was developed by Kun Chen and Christian. So that's what they did. They say, okay, we can go to sufficiently high order, guarantee the convergence of our answer with good arrow bars for homogeneous electron gas. And that's what we're getting. The product of z squared times m star divided by m, that's the curve. And you say, oh, looks like in conventional treatment, we're missing a factor of 0.65 in front of the exponent, in the exponent. It's a total disaster for any calculation. This is z squared times the mass renormalization. Oh, sorry. That's the correct statement? Yes, sorry. No, just one. No, I'm just saying, okay. Yeah, I will say it. So just first, I just incorrectly labeled the idea. The idea is to have z squared times m divided by m, but z itself drops to 0.65. Z squared is even smaller. So you say, oh, maybe m star or m will compensate for this. But you see that 0.65 squared, okay, I was wrong. You're missing a factor of 3 in front of in the exponent. It's not disaster, it's disaster squared. So that's where we are. So that's what you are missing. You say, okay, looks like we're getting further away from understanding. Well, but we have more luck with understanding, for example, the effective mass renormalization. If you do naive GW approximation, also kind of popular material science method, yeah, the effective mass is renormalized. Maybe you say, okay, not significantly, but say by 10%. Compared to z squared, okay, almost nothing. Well, but the correct calculation also done by Christian and Kun, well, it says, okay, well, depending on different tuning and theories, well, the correct answer is given by red points, now calculated to even high accuracy. This was one of the early calculations. Now the arrow bars are much smaller. So the dashed line is more or less within the arrow bars. The width of the line is the effective mass. It's actually much smaller effect. And for RS equal 4 or 5, the effective mass is more or less ideal electron mass. Some kind of strange effect in the homogeneous electron gas that despite very strong Coulomb correlations in the system, the effective mass renormalization is almost nothing. Almost nothing, I say, okay, well, at this level of few percent, and for large RS, going down to almost 1%. So at least, okay, with effective mass renormalization, maybe we can ignore it, but not the z squared. So that's one thing which you have to worry. Well, the second one, which I already kind of mentioned, but let me explain kind of what's the essence. Well, if I do, for example, the following assumption, how electrons interact, starting from very high frequencies. And that's what was done by early kind of guys, Tolmachov, Shirkov, Anderson, Morel, Tolmachov. So that's what you assume, that this is true for very high frequencies, and it's true to very low temperature, very low frequencies. As if Coulomb interactions are completely screened already at the Fermi energy. Well, so that's what they did, but formally this is static approximation, which says if you give electrons infinite time, which means zero frequency, yes, they will screen Coulomb interaction, but it's a dynamic process. So at very high frequency, of course, Coulomb interactions are unscreened. So you probably do a better job if you just account for the fact that, well, okay, Coulomb interactions, the way how they screen is developing in frequency. And that's literally the proper curve. You start with, for example, if momentum is much smaller than K Fermi, it's very strong repulsion, because Q squared in denominator at very high frequencies. Well, but then once you go to plasma frequency and below, you start the screening process, and you end up somewhere here. Well, in fact, the effect of Q now is just minimal compared to Thomas Fermi K squared. It's pretty accurate. Well, of course, if I start with bigger value of Q, it's slightly smaller Coulomb interaction because it's large Q. Well, but still, it will drop to a smaller value. And from the theory of superconductivity, it's well known. The moment you have a potential which is frequency dependent with much smaller value at zero frequency, at the Fermi surface, they would still produce attraction. The gap function will change sign, and that's literally what people were thinking about electron phonon coupling in the first place. It's a constant coming from Coulomb repulsion, not the true. Blue curve is the true one, assuming a constant like here, not frequency dependent, and this deep is simply because of the electron phonon coupling. And that's precisely how the previous theory was working. Not saying that Coulomb interactions always outpower electron phonon coupling, not at all. Just saying in bare terms, it's always repulsion. It's just weaker repulsion at lower frequencies, and that's why you're superconducting. But you have the same from screening. And from this picture, that's precisely what Takada, Rachel Sham did, and we did, I know, a couple of calculations the same way. The answer is the same. Just because Coulomb interactions have this structure in frequency, they produce a pairing glue in the S channel for RS bigger than 2. So which means the previous reasoning is totally wrong. You do a better job. It's not a positive pseudopotential, it's a negative one. We're not solving the puzzle, we're making it worse. But remember about the Z factor. You say, oh, maybe because electron-electron interaction now is helping you as a glue, the Z factor is hurting you. And that's what actually is making TC smaller. Maybe. Okay, well, this is more or less the outcome of the calculations based on dynamic RPA. It says, okay, well, if you do naive dynamic RPA, it's the green line. Well, there is slightly better treatment by Kuchen and Overhauser, which is taking care of leading vertex corrections. And you see that the curve still changes sign, but for RS equals 3. At this point, you start wondering, okay, yeah, maybe small RS answer is okay, but large RS answer is not reliable. This is mu star, which doesn't include any Z factors. This is mu star coming from interactions only, no Z factors. Z factors are separate. In this story so far, I'll just come to the right treatment. This is more or less historical account, okay, how we come to different pieces, kind of being present, but ultimately, the sign, of course, has nothing to do with Z squared. Simply the magnitude, of course, if I multiply by Z squared, just scale it down by a factor of 3 for large RS. Then you say, okay, well, there are more players in the game. Even if I decide what is the bare electron phonon coupling, I'm not saying that that's how you compute it in material science, not at all. I say, okay, if you have a bare coupling between electron density couples by Coulomb forces to the ion displacement. Well, I will simply pull out the Coulomb part outside, and whatever rest, let me call it G. So this is full electron phonon coupling. I just separate them a little bit, you'll see for the reason. Okay, so just pure rewriting, nothing more. So we say, okay, I have coupling between electron density and the displacement of the atom. Well, but then you have displacement of the atom. So this is just my parameterization. That's why I write it on those way. Okay, this is Coulomb interaction coupled to density. But then those electrons can propagate, form a bubble, propagate. This is Coulomb interaction, form a bubble with vertex corrections. And you end up with the incoming and outgoing electron, also addressed by the gamma 3. So looks like if I want to take care of Coulomb interactions correctly, I have to first to compute the entire what's called W function, which is charge response in the interacting Coulomb system. Otherwise, I am mistreating. So the electron phonon coupling is not just this part, but everything starting from Coulomb interaction, full polarization, and ending up with gamma 3. All of this has to be done. And there is no perturbation theory. The vortex interactions in the Coulomb gas are 41. No, you start with displacement of the atom. After that, you have phonon propagator, and then another electron to which you will couple.
The question I'm asking, if it's really kind of a localized potential, can I think of this dressing as some kind of Friedel oscillation?
Sure, you are allowed. It has to be done, I'm saying. Now, of course, when people do material science code, this is more or less automatically included in the calculation. So they probably do this job already most explicitly in the definition of the electron-phonon coupling. So but if I want to talk kind of in Bayer terms, before I say, okay, how many electrons? Because all of this says, okay, well, the answer definitely depends on how many electrons in this sense. So, okay, if I decompose the problem into how one electron will couple to the ion, and then I add more electrons, I have to do all of this. Just simply breaking it for simplicity into Bayer terms and renormalized terms. So that's another player. And the final piece. You say, okay, yeah, of course we did Bayer-Coulomb interaction, but then there was an argument by Takada and Rachel and Sham that you have to add bubbles for screening. Of course, I draw one bubble, but you can draw as many as you want. So, and that's his dynamic RPA, representing the dynamic RPA. Then essentially this one plus this one together, that's probably present here. Then you have vertex correction here, scattering in the particle Hall channel, and then whatever you can imagine drawing in all channels. That's only part. Then from Tolmachov and others, we say, okay, yeah, but if you want to define effective coupling at low frequencies, you also have to do reducible diagrams. You also have to include in the definition of effective coupling at low energies also Cooper channel with energies bigger than a certain cutoff. And then I will use the correct number for lower frequencies. But I also have to include those diagrams. Now just almost every line which I am drawing here, which is then reducible in the Cooper channel, is the sum of all those. So all of those together, assume this is now just one dashed line. It's very hard for me to draw otherwise. Just assume that the entire upper row, that's just one piece here, then it's repeated here. And that's what I'm trying to illustrate here. So I have also to do reducibility in the Cooper channel to sufficiently low frequency cutoff, and then I will introduce the proper understanding of how electrons couple at low frequency. All of this has to be done because there is no small parameter. So that's what's missing. So apart from talking about some static RPA, we have to account for the fact that screening is dynamic. It cannot be static RPA. That's definitely dismissed by previous calculations. You have to count about effective mass. We're lucky. You have to deal with the Z factor. You have to do gamma 3. You have to do screening. And you have to do all of this. So it was done. But we did it for homogeneous electron gas. Again, kind of this is the same technology which was developed by Kuhn and Christian. It's simply high order diagrammatic Monte Carlo with variational parameters. And you can see order by order by order that, yes, by order 6, you have converged results. Now, just what do you compute? Well, by definition, what I was showing you, we want to understand quasi-particle scattering. So I can immediately plug it into the Migdal-Ashberg machinery. For this, I have to compute a object which is the product of Z, gamma 3, M star over M, and W. This was my picture for screened electron-phonon coupling. So what is the product of all three of them in a row? So that's the effective theory which I have to use. So we did diagrammatics for the product of all three. Why for the product of three? Because many, many things are canceling. Remember, Z factor was severely suppressed. But gamma 3 is enhanced. And there is a pretty much very severe cancellation between diagrams for Z and gamma 3, known in many different other contexts, but you have to do it. So now just if you compute all diagrams for the product of all four quantities, that's the final outcome. You see dots. So those are points computed for different values of RS, 1, 3, 5. So all of this is kind of done and computed. And then you say, okay, what are the lines? The lines are very well-developed machinery of density functional perturbation theory. It has phenomenological parameters, fine-tuned to what is known about the properties of homogeneous electron gas. People invested decades in understanding this, tabulating it, extrapolating the results, testing them on the materials, and they have very good understanding what to do using exchange correlation kernel. So that's the quantity which is coming from density functional perturbation theory. And that's how they would model the same quantity. I would say just almost perfect. So this part is actually very well done by material science people. Even though it was never established and confirmed, you can't do it for sure for the homogeneous electron gas because this calculation was never done diagrammatically for the product of the four. We confirm it's a good procedure. But the other one was never done with any level of accuracy. Now, what do we need for gamma? For the effective quasi-particle scattering at low energies. That's what I have to put into the Migdal-Ashberg machinery and stop wondering about electrons coupled by Coulomb forces. Completely forget about Coulomb forces, just using one number. For this, I have to compute effective coupling for quasi-particles. So it's z squared, density of states, and gamma 4, which is the sum of all the diagrams which I was showing you before. Then you say, okay, should I worry about reducibility? The answer is no. You compute gamma 4 from all graphs possible. Reducible in the Cooper channel, not reducible in the Cooper channel, just do the job for sufficiently low temperature below all characteristic frequencies of the Fermi system. It's definitely doable. But once you get the Taylor series for gamma, you interpret those Taylor series. They start, for me, they start from n equal 1. That's the first interaction. Xi, you say, what is Xi? Xi is simply counting orders in the perturbation theory. So Xi is 1 is the physical answer. And when I mention Xi, this is just to say at what order in the perturbation theory you are looking at the answer. So physical answer says put Xi equal 1, you're done. This is simply just to differentiate between different coefficients in the Taylor series. Okay, so you compute gamma as Taylor series in the interaction. And then you simply interpret the entire Taylor series as Taylor series for mu star according to this formula. Well, of course, you understand if it's Taylor series, Taylor series, Taylor series, one Taylor series can be expressed through the other Taylor series. That's the formula. Yeah, of course, you can say, okay, mu1 equals gamma 1. Mu2 equals gamma 2 plus gamma 1 squared times log. And you just keep going. So it's a kind of trivial rewriting, but there is a lot of cancellation between different terms. So even for gamma, maybe you don't have very nice convergence. We found a very good convergence for mu star by doing this procedure. Again, you have to do it for all four, because there is a lot of cancellation which happens on the way. Vertex corrections are part of gamma 4. They are the diagrams which I was showing you. So just everything goes in. And that's how you more or less, you say, okay, why do I have this fitting? You undo the Cooper channel. You say, okay, whatever was probably overdoing in temperature for the Cooper channel, I'm just taking it back. So omega c is simply a good parameter to tune how quickly those series will converge. Well, of course, you can immediately say, okay, well, if I'm doing mu star according to this formula, then mu star here, you say, okay, yeah, it depends on omega c. Not nice. We know that mu star depends on omega c. But why don't we have a parameter which allows you, just in case, because you say, I am running my code, RS is the same, but I want to use a different mu c. Shall I recalculate all the data? The answer is no. Simply reparameterize this equation in terms of mu f. And if I just do this, it's just one is exactly the same. So that's how mu star depends on omega c. Simply mu f is much more convenient parameterization for mu star for whatever omega c you want. So that's why we write down all our answers for mu f. Again, mu f is not a physical parameter in this sense. The physical parameter is effective coupling at low frequencies. Put here the frequency you want, you'll get the effective coupling at this frequency, assuming this frequency is below all other characteristic scales. Yep.
Suppose it's no normalization at all. Go back to original level 0 theory.
Yeah.
You get mu star standard formula, but then instead of mu f, you get flow interaction times density of states. How do you get local temperature? Can you use your C-band, please?
Because gamma contains same logs. Now again, that's the formula you have to look at. You say, okay, gamma is all diagrams reducible in the Cooper channel. It contains all the logs. And then you say at low temperature, it's supposed to behave as if some effective coupling and then Cooper channel. And that's precisely what I would like to know. I would like to know what is controlling coupling in the Cooper channel. And that's how you start computing mu instead of gamma. And then this is kind of trivial reparameterization to have something more universal, just in case you want a different omega c without recalculating anything. So this job was done, and here that's more or less how the answer will look like. You go order after order after order after order. Boris was showing this, but not everybody was present. So we just see that, well, if you go to lower and lower temperature, first, mu star is not a function of temperature. That's precisely what you want. You go to, in the calculation, you go to lower and lower temperature, but you produce a number which is temperature independent. That's precisely what you now have to use in front of the log. That's first confirmation. Well, yeah, this is already 4% of the Fermi energy, so which means temperature was already low, and you can go to even lower, nothing. And then you simply go to higher and higher order. I know, order 1, 2, 3, 4, 5, 6, but at order 6, more or less, we already see, I know, no difference in the answer. So that's our claim. Okay, not 0.15 for this particular value of RS. This was RS equal 1, 0.165. And that's kind of more or less the summary of all this work. If you have a homogeneous electron gas and you want to claim some pseudopotential at the Fermi energy scale, so then you can use it to recalculate what is mu star for whatever omega c you like. For example, dBi frequency in a particular material. You'll just put here maybe, I know, 2 or 3 dBi, more or less kind of to be sure that you are using it at sufficiently low frequency, but above the typical phonon spectrum cutoff. You'll produce mu star out of mu f. And that's the value of mu f which we are getting from this. Yes, you can say error bars are large, totally agree. The calculation is very tough for RS equals 6. For some properties, as Christian already knows, we more or less start hitting some walls close to 5.2. So this is still reasonable. This is probably too large. Well, but the rest is there. And then you compare what was used in the past. This curve is called Anderson-Morel, or Morel-Anderson. Well, this is more or less saying, okay, coupling between the electrons at the Fermi energy scale is 4 pi e squared divided by kappa squared. So that's this answer. Well, you do static RPA. Static RPA is the orange dashed line. Yeah, not much different. That's precisely kind of the Thomas Fermi is a very good approximation in this sense. Okay, that's here. Well, if you do Takada and Rachel Sham, much better job. Well, it's actually not only low, it changes sign, it just goes negative. But the calculation from all graphs, including particle hole channel, which is compensating for some of the Cooper logs in the intermediate energy range, produces this answer. Well, it's not a small effect. You say, okay, mu f, here all answers are the same. But this is RS 0.2, 0.25. Starting from RS equal 1, you already see the difference. Then it grows to factor of 2 and up to factor almost 3. So that's the differences in mu f. You can say, oh, probably this makes huge difference from material science. Say, not really, because you see the formula. If mu f is getting reasonably large, but the log is large, we don't care much. Because if this number is large enough in denominator, forget about 1, cancel mu f, and your answer is universal anyway. We're simply saying our answer is more universal than was assumed, just because our mu f is bigger. The bigger the mu f, the more universal your answer is, because this mu f will cancel in the denominator. But if you want kind of, now just more or less an advice, if you want to do mu star without computing, but simply using some value of mu star for a particular value of RS in your material, then probably use this parameterization of mu f as a function of RS. Convert it to mu star for the frequency cutoff you want, and use it in your calculation. Okay. So that's more or less the end of the story, how everything was developed for Coulomb pseudopotential, how it actually plays in the S-wave superconductivity. Looks like the prescription is, first, we know what to compute. We explain exactly, okay, what has to be computed, how it has to be analyzed, and to produce the answer. But unfortunately, my bad news is that there is no cheap way. We have pretty good understanding of electron-phonon coupling, just no complaint. Density functional perturbation theory does a perfect job almost within our calculation. So they just do everything right. But when it comes to Coulomb coupling, gamma 4, z squared, and the rest, it's total disaster, out of which you get the same number, roughly 0.15, out of totally different physics. But this has to be done. So for gallium, it's done. We explain, okay, how it works and get the same answer. But if you do the same for a multi-band system in a particular material, of course, none of the answers are universal. It probably will change just because it's not just only RS. Apart from RS, we have tons of different other pieces in material science. So which means they potentially will also change what is mu star if you want to do a better job. But to do a better job, you have to follow the prescription. Yep. Yeah.
What would happen if you make the masses anisotropic?
Nope.
No, there's no nice way to.
Okay. I'll repeat the message. There is no cheap way. So for far, first, we have no data to produce a cheap way. Probably if we have a database of different calculations for different setups, we'll develop cheap ways. So that's more or less how sometimes in the very complex environment, that's how we navigate. We need reference points, which we definitely trust are correct. Then we can understand, okay, how we can work in between and have very good cheap ansatz kind of to produce the answer. So far, I say, yeah, it's the first calculation. You introduce anisotropy in the dispersion relation, see how the answer changes, what's universal, what's not.
I mean, I guess what I was trying to ask a more conservative way of asking what happens in 2D.
Good. Well, what happens in 2D is that nobody had the time yet to run the code in 2D. That's what happened in 2D. So which means it has to be done, and I'll show it on the last slide. It's a good question of leading me more or less to the end. You say, okay, did we try to use it at least for something useful, as Steve saying? If you think you understand the problem, just make some use of it. So we decided to make some use of it in the simplest possible way for people who can do only homogeneous electron gas. So what is the way? We say, okay, take aluminum, assume it's a homogeneous electron gas with known RS. Well, RS will depend on pressure, and simply use our machinery for mu star without any fine-tuning, which means mu star for aluminum at a given value of RS is given by our plot, just nothing else. And then add electron phonon coupling for aluminum, which is kind of well understood, and compute TC. So our first kind of outcome is that first, we're not tricking or fine-tuning mu star at all. It's coming from the homogeneous electron gas. We just borrow what it's predicting for a particular value of RS. So that's our prediction for TC in aluminum. Well, this is zero pressure. It's already better because if you just do nothing and use too much of like kind of machinery, you are missing this, and I think the prediction is close to 2 Kelvin, like 1.9. Yep.
Are you allowing for pressure changes in theta Debye?
I think it was done, yes.
Wait, that was included here.
This was included in the calculation, yes. The calculation is using realistic phonon spectrum with realistic electron phonon coupling from material science code.
Okay, because you were saying it's only using your
Yeah, the only difference is our mu star is not changed in any way relative to the homogeneous electron gas calculation. Yeah, that's the only difference. And okay, well, the blue curve is our data. The rest are experimental data. I don't want to claim anything because aluminum is not a homogeneous electron gas. If it works at this level, we're probably happy, but we're saying at least it's better, and I'm not wondering, okay, what number I have to use, 0.15, 0.1, or 0.2. This is more or less my conclusion, so I'll stop here. So effective coupling in homogeneous electron gas ultimately happens to be repulsive for any value of RS up to 6, which we calculated, and looks like there is no turn back. So it just keeps going up. So far, we just didn't see any trend for this to becoming smaller for larger values of RS. Everything we knew before was total misunderstanding of how the problem works, from using static RPA, then dynamic RPA, and actually not doing anything for larger values of RS. Everything for larger values of RS is important. You have to do Z factor, you have to do gamma 3, and you have to do high order diagrams. Only out of this, you just get the correct value of mu star. Since we have all of this, I have no kind of other advice but to say that, okay, somehow we have to manage with all the complexity of material science calculations, which are now multi-band, not spherically symmetric. All of this is different types of interactions. This is much harder job. But if it's possible to pull out roughly the same trick, at least maybe at the lower, well, the convergence is pretty good. So if we can pull out the same trick up to order 4, maybe we'll have a much better machinery of understanding, okay, how you can now just compute mu star from real ab initio, not just relying on some phenomenological treatment for a particular value of RS, you have to use particular mu star, or it's based on static RPA, as I already showed you. Static RPA just misses the correct answer by a factor of 2 at large energy scale, and then you just scale it by log automatically anyway. So which means your start is a factor of 2 wrong. Because of the large log, yes, you are arriving to the same more or less universal understanding at the bottom, but still, if you want high accuracy, this should be done. Future one is what we have just explained. So we have to, more or less, now I say just, well, it's well understood, so probably it should be done, because there is a lot of interest in two-dimensional materials for a large number of reasons. Probably this has to be done for the two-dimensional electron gas. There is one difference. In 3D, plasma frequency is gapped, which means you have very nice understanding what is the highest energy scale in the Fermi liquid below which you have to finish the calculation. Now the plasma is gapless, and the question is still open whether we'll end up with mu star, which saturates to a constant, or we have to account reasonably well for leading temperature corrections. This is not known. But the calculation can be performed just to see what's happening. So I see it's kind of one of the first directions we have to do to continue, to have well understanding of what happens actually in 2D, how much you have to worry about high order terms and diagrams. Well, second, again, the same machinery can be used not only for jello. We have a lot of different lattice models for which the same would be all very interesting. So you say, okay, yeah, if I start with, say, 3-band Hubbard model, what is the effective coupling in a particular channel? The same machinery can be done for any scattering channel, not only S, but also P, D, and so on. You just simply separate channels, but do the same job. So this has to be done. So I think it's very important. And there are many people who are interested in the problem in CCQ, just, you know, at least the whole group, which would potentially be interested in kind of doing this type of calculation. Well, the ultimate goal, again, this is beyond my training and understanding how to actually pull out the technicality and the difficulty of this. Doing all the same with high order diagrammatics for real materials. And so far, just the only person whom I see capable of pulling this trick is Christian. So that's what I hope will happen, that ultimately we'll be able to compute mu star for realistic material balance structure. I'm probably a little early, but...
Thank you very much. Okay, more questions. There were already some, but Tero?
Thanks for the interesting talk. Besides sort of actually solving the problem, maybe you can try to figure out then what would be kind of desired to increase TC. I mean, it's probably a very complicated question, but...
Well, you see, it's very difficult to do AI on one point. We need training, which means we need to do a lot of calculations like suggested. So we have to do, say, an isotropic in continuum, at least one something. Then probably do simple multi-band models just to see how it works there with Coulomb interactions or contact interactions. Once we have many points, probably we'll start developing understanding in which direction it's better to move to reduce mu star, because right now it's hurting. It's hurting superconductivity. Maybe we'll find out the conditions when actually we can reduce mu star or actually flip the sign. Because that's precisely, I agree that some people say, okay, we need unconventional mechanism, and it comes with the addition, not in the S-wave channel. I say, yeah, it would be nice if we have unconventional mechanism, but in the S-wave channel as well. So probably unconventional mechanism in the S-wave channel is probably not very close to discovering. Well, there are a lot of discussions. Steve is saying, okay, well, how we can achieve high TC. Maybe we understand how to control mu star. We can do the same.
Yeah, Andre?
A little bit more technical side. At the end of the day, although you said that Anderson, Marel, and Pogolov, etc., were wrong, your result is very similar to what they found.
No, it's different by factor of 3. No, it's different by factor of 3.
You started against pretty much.
No, it's mu star is not the answer. The answer is mu f.
No, but we have cancels out at the end.
But then there is nothing about anybody. If whatever is mu star, as long as it's positive and the log is large, then you don't attach the name to something which doesn't exist. It cancels. In this sense, yes.
Was the goal to calculate MF, or the goal was to calculate the whole effect of Coulomb interaction, which not necessarily will...
No. Our goal is to calculate mu star. I am characterizing mu star through mu f, so whenever you want to change the cutoff, you can immediately use this formula. Of course, the mu star is the interesting quantity you care. Yeah.
You can always introduce me of this.
Yeah, yeah.
Knowing that there is so my question maybe is like this. At the end of the day, there is something that looks like cancellation between the effects of Z factor and effects of higher order.
Absolutely right.
Do you have any sense why is that, or is just completely accidental?
Some things we have understanding at the level of simply computing diagrams. For example, you say, Vital-Machov was right in something. And I was actually thinking that whatever we did will never work. Because their log, if you do whatever was done originally, mu f, just look at the structure of the formula. Just imagine your mu f is a 41. You say, OK, if mu f is a 41, and this is large log, you're outside of convergence radius. What the hell did we do? And I was thinking that's precisely what we'll have in the calculation. So if we do reducible diagrams in the Cooper channel, we'll immediately hit the wall because we'll have a large number in denominator and we are completely outside of convergence radius. Everything will break down. But then we have Kuhn. And Kuhn said, yeah, I already computed some of the diagrams and there is particle hole scattering and it has an opposite sign. It's not a log. But you see, if the log of 1 or 200, it's what? 4, 5? He said, yeah, but if the other diagram has pi or 2 pi, it's 6. So I simply at the intermediate scales between Fermi energy and Fermi energy divided by 10 until I pass the plasma frequency. All diagrams turns out to be important, and whatever was this Cooper log is actually not working at all in the intermediate energy scale. Cooper diagrams are completely annihilated by particle hole scattering with the opposite sign, and the ultimate outcome is plus.
But yet the result looks pretty much the same as the original one.
The result
except that mu f is larger.
that's why
Mu f
I
is
will
larger.
keep pushing with the same button. The result is totally different from what was known before. But if you recalculate it using this formula, the answer is universal 1 over log.
Yeah.
Well, I'm not responsible for, because this is just a reparameterization of the answer. But the answer for mu star, which is repulsive, says it's impossible to predict because that's the correct curve. At the minimal level, the blue curve is the right one because that's the dynamic RPA. It's much better than static. And that's what the blue curve is predicting. Yeah, it's totally different.
The observable quantity is mu star, the observable quantity, and mu f is parameterizations that you like.
Yes.
Of course, I know. Just, well, we simply explain why mu star is repulsive, even though if you do lower the perturbation theory,
It's
you
the
get
same
negative.
question, why there is a cancellation of terms that doesn't allow blue line to go
Yeah,
down
I'm
and become
explaining the
negative.
cancellation comes from particle hole channel, which is canceling the particle-particle channel. That's the actual reason for people doing diagrammatics. Yes.
Okay, let's go to the next question. There was one here and then Andre.
It's okay. I'll-
Okay, Andre.
I didn't get the message for aluminum. For aluminum, you're saying it's quite a good match, right?
Yep.
So aluminum is empty lattice approximation, right?
Yep.
So aluminum is basically free. Why,
That's pretty-
how does it go for indium? Indium is a little bit.
It's a good. You see, well, you're asking a person who never did a single material science calculation, except participating in. No, I know. Except participating in this one as a free electron gas, with a realistic electron. Yeah, we also did calculations for simple.
It's just a little bit.
No, I understand. Yes, but we also have aluminum, potassium. Yeah, we did this type of calculations. Again, you say simple metals, empty lattice, precisely. So that's also we did, and we say, okay, that's what you would expect for TC. For example, in those simple metals, maybe under pressure, or why they're not superconducting yet, because transition temperature is below 10 minus 50 Kelvin. We did this type of calculations. Aluminum is just one example. But they're all simple metals when we say, okay, maybe it's reasonably well to use homogeneous electron gas calculation to produce mu star. That's all.
And then if I add the lattices of perturbation, what happens?
Yeah, nobody knows. Nobody did the same type of calculation for more complex setup.
Where you wanted
Yeah. So in the final form, so I got a bit sidetracked. On the final slide, WC is the Thomas Fermi screening, or plasma frequency, or whatever. Yeah, in the logarithm. Is that right?
Omega C is whatever you like.
Whatever I like.
No, just mu star depends on the frequency at which you would like to define
Yeah.
Coulomb coupling, effective Coulomb coupling at this frequency. And that's
Order of the bifrequency. Right? It's order of the bifrequency.
Yeah, usually people just say, I don't want to compute anything to frequencies higher than 5 dB. Then you put this as 5 dB and just run full Eliashberg type theory up to frequencies 5 dB, which means you take care of Coulomb interactions as a constant, but phonons you're doing.
But you substitute this into result for TC, which is exact. So you are doing exact calculation. Why the scale omega c is then not fixed exactly?
At what?
You use mu star to calculate TC.
No,
You have
no,
all diagrams.
Andrei, no. Just, again, I never said anything about TC, sorry. Mu star is effective coupling in the Hooper channel coming from Coulomb interactions at low frequencies. That's mu star. TC for repulsive mu star is 0. There's no TC.
But you
No,
add,
But if you add electron-phonon coupling, you can use my mu star to produce TC. That's precisely what we did.
which means
for
that
illusion.
omega c is fixed.
Omega c is fixed by several dB frequencies. Yeah.
Okay.
But you can use any other value, it will work as well. Yeah.
Okay.
As long as it's
question.
smaller. Sorry.
So imagine you want to solve big Eliashberg equations with Coulomb interaction without doing this mu star approximation that you could usually do. So just consider like convection elements and so on. What is your message here?
You'll get at okay.
So we should be good to do it at RDA level, be good to do it at RDA dynamic, or what should we do?
No, I already answered the question. So you can do 5 mistakes in a row and get a reasonable answer. So you do static RPA, totally wrong to start. You ignore Z factor, wrong by a factor of 2, also good. You ignore gamma 3, renormalizing the Coulomb interactions, also not bad. And you also ignore scattering in the particle Hall channel, which is outrageously large. And you end up with a roughly correct answer. So cheap way is what is done now. And we know that some of the answers are pretty reliable, and sometimes you are almost there with correct prediction of TC. I'm simply explaining how this is happening. But this procedure is no way forward if I want to have an alternative mechanism coming from Coulomb interactions helping TC. Because for this, I have to change the sign of mu star. And then I need a protocol and machinery to compute it properly. Because if I start with static RPA, I'm nowhere. It's just repulsive. It's not much. So the material science would say it's 1.9. We're getting 0.9. The correct answer is 1.2. So everything within 50% up, we have 30% below. At the level of mu star, it's probably, I know, 1 or 2 in 100. Oh, just I cannot immediately say out of my head, because electron-phonon coupling also changes, so I didn't. Probably its RS is changing within 20%. No. We are using slightly worse because, okay, in this prediction, sorry for time, but I'm not responsible for terminating my answers. You start, okay, sorry, I cannot reach it. That's where you start, at 1.9. And then if you use a constant, probably you have some curve. Again, this is by how much you want to miss. We start closer, but slightly below, and that's our data. You will start from the ceiling and probably produce some curve, which is also, of course, bending down. But by how much you will miss the answer, okay, maybe by saying 50% or a factor of 2, roughly.
All right. So I guess that was a very lively discussion. So let's thank the speaker again.